In this first background lecture, we will explore the topic of plate tectonics and continental drift hypothesis. Plate tectonics is a guiding theory of Earth science. It answers multiple questions about the history of the Earth, such as why we have rugged mountains like these. It tells us why mountains like Mount Everest have rocks at the top that contain marine fossils. Plate tectonic theory tells us why we have volcanoes and why they occur where they do. It tells us why some volcanoes, like Mount Rainier, are dormant but not extinct. It tells us why we have earthquakes. It also tells us why different continents have different types of animals on them. To understand how the theory formed, we need to look at the history of tectonic theory. Prior to the late 1960s, many geologists believed that the positions of the continents and ocean basins were fixed. Continental drift, a hypothesis designed to explain continental movement, was first proposed in the 20th century, but initially rejected by North American geologists. Continental drift was an idea before its time. Alfred Wegener first proposed his continental drift hypothesis in 1912 and published The Origin of Continents and Oceans. His hypothesis stated that a supercontinent consisting of all of Earth's land masses once existed. He called this supercontinent Pangaea and hypothesized that it began breaking up about 200 million years ago in the Permian period. This illustration shows a modern reconstruction of what Pangaea looked like. The smaller paleogeographic map is Wegener's Pangaea, redrawn from his book published in 1912. Based upon his observations, he was remarkably close in his location of the continents that made up Pangaea. We're going to take a look at the evidence that Wegener used in support of his continental drift hypothesis. The first line of evidence was the jigsaw puzzle fit of the continents. Notice how closely South America and Africa fit together when you include the continental shelf, which is the flooded portion of each continent. The second line of evidence is fossil evidence. Wegener noticed that identical fossil organisms are found on continents now separated by vast oceans. South America, Africa, India, Australia, and Antarctica make up Gondwana. Fossils of Mesosaurus, a freshwater lizard from the Permian, are found in South America and Africa. It would have been impossible for this animal to swim across a saltwater ocean if the continents were separated then. Lystrosaurus is a mammal-like reptile from the Permian. Lystrosaurus was obviously not a swimmer, yet its fossils are found in Africa, India, and Antarctica. Finally, all parts of the seed fern Glossopteris are found on all 5 of the Gondwanan continents. The third line of evidence is rock types and geologic features. Notice in the map illustration that the mountain ranges in North America, Africa, Greenland, and Scandinavia, which are the same geologic age, would only have formed through collision of the continents when they were together in a supercontinent formation. The fourth line of evidence that Wegener noted was ancient climates. On the top map, you can see where evidence of ancient ice sheets and coal swamps are located today. These climates have been dated to the same age and could only have formed if the continents were together. Of special note are the ice sheet data. When continental ice sheets form, they flow outward from a central point, and they leave glacial deposits as they do so. When we reverse the flow direction of all of these deposits on South America, Africa, India, and Australia, it points to a central location in Antarctica, as you can see in the lower map. There were objections to the continental drift hypothesis that caused a great debate. The greatest objection was that Wegener proposed no viable mechanism for how the continents moved. Wegener incorrectly suggested that the gravitational forces of the moon and sun were capable of moving the continents. He also incorrectly suggested that continents may have broken through the ocean crust. There was strong opposition to this hypothesis from all areas of the scientific community. This is the end of Lecture 1, Part 1. In Part 2, we will explore Earth's composition and plate boundaries.